leadership because I think it's great that he's courageous enough to challenge us on these things and patient enough to stick to it. And as I'm introducing our next speaker, Soheil Nazarian is also one of these people that is certainly a stick-to-it kind of guy. He's been at this for quite a while. He's put up with a lot of resistance from the DOTs, whether it's or no matter where it is in the country. We don't tend to do things to make change very easily, and it takes a whole heck of a lot of patience on the part of people working for decades. And Soheil's one of those people. So we're grateful he's maintained patience and partnership with us for many years. So again, it's good to have you here.
Oh, I appreciate it. Yeah, sure. Actually, he needs to give this talk. I don't know why I'm giving it, but but I appreciate the kindness and the partnership. I always learn when I come here. Okay, the same theme that Dr. White, Dave talked, let's keep going with it. Okay. You cannot, the first thing I have over here is we are just going to start focusing on the moisture, one part of the process control. And there is no way you can separate construction, design, and material and expect different results, If these three guys don't talk to each other, well, the state of practice would state of practice. Because as soon as we say mechanics, mechanistic, the designer needs to be talking to the laboratory needs to talk to the construction and quality control. So I want to re-emphasize that theme. It's too late, I know I'm the last thing before the party. So let's see what we're going to do. Okay, let's go back to the fundamentals, degree of saturation, what we deal with. Usually we want everything, the indication of quality is to be close to the optimal moisture content. And usually what we do, when you do the Proctor, the degree of saturation at optimal moisture content is around 80 to 85%. So just give a benefit of the doubt. We say that if you are a material with a degree of saturation between 7 and 90, it's a good material. If it's between 95 and above, as a geotechnical engineer, we consider it saturated, And if it's blue, it's a fantasy land, we cannot have a moisture content more than 100%, but if you use the theory, you get more than 100%. That's land of 10,000 lakes, the lakes. Okay. And then if you do it too dry, it's not good enough as well. So we have a margin over here. So I went ahead and I was playing, and what I have over here is the dry density versus the moisture content. These are the things that we use right now for process control, quality control, acceptance, right? And the numbers are kind of goofy because when I have a 5% and 150 pounds per cubic foot, I'm talking about a very good base. When I'm talking about 25% and 90 pounds per square foot, I'm talking about a clay. So I color-coded this matrix with this colors that you see over here. So if I add too much water, I'm going to be in this area, and that will be what Dave is showing you. You can go horizontal, vertical, left, right, anything. You're not going to compact anything. But if you see that the margin of error, when you have a very good material that you pay a lot of money for it, that's a base. This is select base. You have very, very little margin of error with the moisture content. Now, when you get to the clays, these are the fat clays we're talking in this area, you have a little bit more margin of error. You can add a little bit of water and a little bit less water. And if you look at the most of the specification, we get plus minus 2% allowance to the contractor. So it may be good for the clays, but when you get around here, we're going to have a lot of problems. Okay, so just have that in mind. Now, we have to measure what's the impact of the moisture content, or if you're designing or whatever you're doing, you have to have a modulus. We are talking mechanistic. So the best thing you can do, you can run get the material and run the lab test. We signed the survey as part of the 10-84, and we asked them what's the impediment to do mechanistic design. They say resilient modulus testing. It was a little bit confusing to me, right? You cannot be mechanistic without testing, but that's the feeling over there. Now, you can be a little bit pragmatic. You can make a catalog of the materials and have numbers, typical numbers. You can use it. You can estimate it based on the relationship, or you can do what a lot of people do, whatever the default is into the program that they're using, they're going to go with that. I know text out better than the rest of the world. I know that, the modulus of the base, doesn't matter where you are, is 30 KSI, because that's the default. And subgrade doesn't matter from El Paso, which is on the rock, or Orange, which is saturated, is 10 KSI. So, and then if you're going mechanistic, Dave talked about this, you have to have a equation, a constitutive material model to show it, and that's what we use. So this is from the best to the worst that we're going to do. So let's talk a little bit about laboratory testing. So basically what we do in the laboratory, we just go and usually we use Proctor. We prepare a specimen. We do it as add a certain amount of water after we get the moisture density curve, and then we put the same effort to prepare the specimen. So if you're doing a standard Proctor, you put so many drops at a certain level and so on and so forth. And then you put it in the machine, resilient modulus. Now this has a very huge impact. The stiffer it is, the better. So the more money we put into it, the more stainless steel you buy, the better the results would be, because some of the stiffer material, the machine moves more than the specimen. So you have to be careful of that. But nevertheless, there are a lot of good equipment that you can get. So the first question that they will say, what loading sequence you're going to use it? I am old enough to know 6th version of it. All of them are in the same database. Okay, this matters. So one thing that we have to do, we just have to go ahead and find a standard and just go with it, because it's a convention. It's not going to be. Why I'm saying that? I'm showing you there are class 1, class 2, class 3, class 4. These are the type of materials that we have in Texas. I didn't show. We go all to 6. I just eliminate 5 and 6. Okay, just for the simplicity. And what I'm showing you so is the stress path. We start the test and what we do with it, till we get to that. These are the lines that I'm showing you are the failure envelopes. Okay, so as you see, I cannot test class 5, class 6, or class 4 with this specification for Texas, because they fail. The stress path goes over the failure. Now, 128, it gets a little bit more severe too. I cannot even test completely level 3 because I'm going. Now, for the other ones, the closer I get to the failure and the wetter the specimen is, the more pore pressure I'm building. So I'm going to get a different pattern. The way these zigzags go, again, I'm in between you and the cocktail, so the more these zigzags go, the more the stress path gets complicated, and the more conditioned the specimen, the more the results would be different. So you have to consider these things. So basically, the bottom line is, I summarize it. The state of stress is important. The moisture content, suction, degree of saturation, these are all the same parameters. The best thing to do is go with degree of saturation, but I personally like moisture content better because I understand it better. There are 2 moisture content that I'm very interested too, and I'm going to just elaborate on that. At compaction, that has a huge impact on what you're going to get, and at the time of testing, these are 2 are important. The density is important too, especially if you're going to the degree of saturation, because density is impacting your degree of saturation. So degree of saturation is good because it considers density and moisture content, but at the same time, you need to know both of them accurately. and I guess gradation and plasticity. So if you look at the calibrated models for estimating, there are all these parameters, and depending on which model you use, you know, there are more or less of these parameters coming into the play. The fundamental ones that we want to talk about is one is the MEPDG model. This is the Zapata's work. This was in the original model, and in 2010, I believe, right? I think in 2010, the modified version came out that considers the type of the soil, the moisture content, having the percent passing number 200 and PI into the system. And this one, the one that is based on the soil water characteristic curve of the soil, this is probably the most fundamental, the best one. We have a little bit of work to do to convince people. You need some marketing. This is a wonderful equation, but you need some marketing. These are the two that we are using. So I'm showing you some of the results. This is a number of soils that, you know, we tested it, you know, from gravel, well-graded gravel to high PI clay, and you can see the result. I'm just basically M over a moisture content, and this is how far you are from degree of saturation. And you see two branches. Usually, when you do on the lab, this gets severe because I told you, you start building more and more pore pressure as you get wetter and wetter. So the material is obvious. If you use MEPDG, this is the state for all the materials. Again, you see you're going to have some drops over there. If you want to look at the error that you're going to get between the model and the measurement, and you see that despite the best model is when you use the Zapata, assuming that WPI is equal to 0, at least based on experience. We have tested more, and that has worked, at least based on the way we are running the test, right? I told you if you run resilient modulus, we run T307. If you run another one, the model would change. And then we go, of course, to the field. That's the goal, right? You know, you just want to monitor it and measure it and predict what it's going to be. We can measure the modulus I'm showing you during construction because that's near and dear to me, but you can easily do it after the fact when you're evaluating, especially with FWD and running. And if I look at the same thing, we just made some specimens from that. Again, you see that for the materials that we put in the field, the Zapata with WPI equal to 0 had the least error, at least for the conditions that we have. But if you look at it, you know, the same density, same moisture content that we put in the lab and in the field, we have different trends. I didn't want to bore you, show you all the details, but you can see. Just let's go back a little bit on the moisture. Some of you have seen this and you're sick and tired of it, but I like it, you know. Okay, so this is what I'm talking about, the clay, and let's do an experiment. We put it at the optimal moisture content and we let it dry. This is what happens in the nature. So we didn't put any sun or anything, you know, we didn't artificially, we just let the room sit in the 70-degree room in the shade and dry. So we have a lot of patient students, and some of them, they still talk to me. So, okay. So you see that when I started the test, I'm getting 26 degrees. I'm letting the specimen dry, 26 KSI, and by the time that I get to 70% of the OMC, it's 100 KSI. So I went by a factor of 4 by letting it go from optimal moisture content to 70% of optimal moisture content. Okay. Now let me do the second thing. Put it at 20% above the optimal moisture content. This is usually plus minus 2% we allow. So at 20% moisture content, testing at 20% above optimal moisture content, I start getting a 14 KSI. But by the time that we wait and we let it get to the 70% of the optimal moisture content, now the modulus is 137. Okay. Now, if I put it at 2% dry and 20%, 80%, and then let it dry, you see that you don't see much the effect of moisture content. So This is usually what the contractors, I used to be a contractor at one point, we love to do. We just like to go wet as much as possible and slush, roll it so that it gets smooth. And this is what probably we want to do. The problem with this one, it's going to get more brittle. You have to be careful not to crack, you know. So the bottom line is that there is a large number of moduli fall in the area that you know is permissible for us. So you see that, so you have too much moisture content, you have to worry. So process control, keeping the moisture content at the beginning during the construction as close as possible to the optimum, or a little bit dry, it helps a long way to get less fluctuation in the modulus as the time goes by. So this is, I'm showing you the results of all of the different models, and in this case, again, modified MEPDG for the fine model is this is the one that is after the fact. Now you have the data, you can do a best fit to the model. So this is what we found for a lot of soil to do it. I want to get it over here and show you what's going to happen when the material dries. So this is the material, you know, I'm just showing you over here the moisture content at the compaction, moisture content at testing, and over here I have the modulus at the time of testing versus modulus at the time of compaction. So, and we let the material dry. We don't let the material wet because it's difficult to control it, but drying we can let them naturally. One thing that you would see, we have a trend for the subgrades and we have a trend for the base. You remember at the beginning I showed you that you have to control the moisture very, very well for the bases. You see the consequences over here. First of all, see that I'm going as high as, by the time that I let it dry, 4%. I'm 40 times higher modulus than that I had. The other worrisome thing is the unpredictability of the numbers. You know, it gets a lot of scatter because it's not uniform. So we try to moisten. For the base, you see, for the subgrade, you see that now I have a better trend, and I have some scatter over here. But you see, I can get a factor of 10 difference. So during construction, this is very important. During the life when you are doing your model, this is important too. So these are, so the moisture is a area that we need a little bit to work a little bit more on it. And you know, first of all, we need a good, reliable sensor to measure. That's Nancy. I'm coming from my TRB side, the instrumentation community. So just this is a little bit. I hope I didn't overextend my. I live in El Paso. It's awfully lonely. I'm just trying to entice you. This is our campus over here. And this is significant. This is a Buddhist temple that was dismantled stone by stone from Bhutan. And they brought it over there to our campus and put it back together stone by stone. We had some of our friends from other religious persuasions, they really didn't like this for a while, but now everybody likes it. It's a beautiful building sitting on the campus. So all I'm saying, you know, come and visit us. And I'm going to just give a couple of conclusions. Impact of moisture, as you see, should be considered. There is no question about it. Degree of saturation is the best way, or the suction is the best way to go. Right now, I think, in my opinion, based on the marketing of the material, we can go with the moisture content until we can market it better to the community is maybe a little bit more pragmatic. So basically, we need laboratory testing for major projects, and we need quality control, especially for the moisture at the big projects and small projects. And I'm a geotechnical engineer. If I want to build a $10,000 slab, I go and spend $1,000 to do geotechnical work. boggles my mind. You guys led a $50 million project, so you don't have $2,000 to run resilient modules, you know, just. Anyways, can I be a grumpy old man? Or? Yeah. That's the end of being grumpy old man. Okay. With that, again, I thank, I'm lucky enough working for TechStat. Since 1981, I have been continuously on the payroll of TechStat. They pay for my education, they pay for my mortgage, they put my kids through college, so. And we have been fortunate to have him, and Min Road, the partnership will really mean that, we really, when people say you can't, we can come and talk to John and other guys from MinDOT, and they see that no, there's hope. You can. And of course, a lot of the things I showed you was funded by NCHRP, so we have to thank them. And again, come and visit us. We look forward to it. Yeah, that's a minor. Yeah. That's our logo. We are Utah Miner, so this peak is our thing. And so if you drive on the Interstate 10, you're going to see that next to the road. So turn right, you're going to come to my office. Any questions? Just one last trivial. Honestly, I can see Mexico from my office. So. No, seriously, we can see Mexico from my office.
Certainly got time for questions. Just thanks for the invitation. We want to, we need to get Texas. We're looking for new NARA partners.
Yeah,
so
sure.
Texas DOT. We want them on board so we can come. We'll have the next February. We'll come to.
Oh, sure, no problem. I talked to them and see.
Good.
Yeah.
So we got to get them on board. So anyway, questions. Some questions for Dr. Nazarian? We get a little time before. We reached the end of our. Maybe just on the sensor.
Sure.
Any new developments on the horizon as far as construction moisture testing? That's something that would get us beyond Bunsen burners or something, or not yet.
There are some new things coming out. They're continuous. We are hoping for a continuous moisture measurement equipment. So we have any innovators in the city in the thing. There are some work. You go back to basics, coming from combining the resistivity and conductivity type measurements that have shown quite a bit of promise. And we are just evaluating it right now, so hopefully if it comes out,
Very good.
I'll let you know. You'll have to come and
well, we're gonna have you
on.
there's a TRV workshop that's gonna focus on moisture testing, and so we're gonna.
Oh, sure.
You're gonna get an invitation tomorrow, maybe.
Oh, sure. No problem. I'll be more than glad.
Anything else? Okay. Well, thanks again for being here.